Good afternoon. Hope everybody is having a great day. And whenever you're viewing this video, I hope things are going well in calculus. There's a decent number of you that I still haven't heard from yet, so I'm hoping that I'll hear from you in the next few days. I want to point out a few things to you as you're watching this video. First of all, section 2.2, 2.3, and 2.4 homework is due on Friday. And so please start getting that together. Remember, I want a PDF version of the homework that's listed in your syllabus is due for a grade. So I don't want all of the 2.2, 2.3, and 2.4 homework, just the problems that I specifically asked to have turned in for a grade. Those are the ones I'm looking for. Also, don't forget that there's an extra credit assignment. I have heard from some of you about that. That's good, and I've tried to answer you. If you've responded to that, if you'll look at, that's also due on Friday, the 22nd of September. If you don't know what the extra credit assignment is, please go to the first page of the notes from the lecture on September the 18th, and you'll be able to find the directions on what I want you to do. It's just a matter of sending me some information, and if you do that, you get 5 points on the first exam. So definitely a worthwhile little assignment to do, because it'll take all of maybe 30 seconds to complete the assignment. So that'll be plus 5 points on exam 1. I also want to point out that the exam 1 review is now online on my Google site. So that would be a great place to go and look for review problems for the test. Remember that the window for exam 1 opens next Thursday, September 28th. And so, let's see, I think I'll write that the exam 1 window runs from September the 28th through October the 3rd. So that means that you can take the test anytime in that window at a testing center in the Lone Star College system. Also, on your calendar, one thing I wanted to mention, and I'll mention this again in the next lecture as well, on your course calendar, there is a lecture listed for September 27th. And so you have lecture on 9/27. But I will not be lecturing on that day because I'll actually be on campus that day. And so no lecture, despite what the calendar says, no lecture on that day. And I will be on campus from 4 to 6 p.m. In my office. So I will be on the North Harris campus, because that's where my office is. From 4 to 6 on 9/27. 4 to 6, sorry. 4 to 6 p.m. on 9/27, and 9 to 11 a.m. on 9/28. So, and my office is in Winship 115K. All of this is in your syllabus. The only change here is that there's a lecture that's listed on your calendar for September the 27th, and I will not be lecturing that day. We will be able to deal with the material. We're actually in a good position to get that material done, and that material from that lecture would not have been on your exam anyway, by the way. So your exam does, and I didn't mention this before, but the exam goes through section 3.5. And so the chain rule, which is what the lecture was going to be on for next Wednesday, will actually, that'll be the beginning of exam 2. Okay. All right. So last time, today's lecture, by the way, is all about, and it's 3, 3, 3, 4, 3, 5. We won't finish all those sections, but we'll do a lot of the material from those sections. And this is all about calculating derivatives. All right, so let's recall from last time. Let's see, so recall from last time that we have a limit definition for the derivative. And the limit definition is that the derivative for a function of x, f prime of x, is defined to be the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. And remember, this is provided the limit exists. There's also an alternate definition too, but this is the main definition that we've talked about for the definition of the derivative. Remember that the interpretations for the derivative that we've talked about so far is that f prime of x gives the slope of a tangent line to a curve at any x value, right? That's one interpretation. Another interpretation is that this is the instantaneous rate of change. Instantaneous rate of change of y with respect to x. So it's how fast the function's changing, how fast the y value is changing with respect to x. Finally, we've also seen that this yields the velocity if given a position function. And we talked a little tiny bit about that last time. We'll talk more about that today. So we know that if s of t is position, that s prime of t is equal to velocity. All right. So those are three interpretations we have for the derivatives so far. All right. So also recall that we talked a little bit about notation, that the derivative of, if you're given y as a function of x, that the derivative of f is, one way to denote that is f prime of x. But another way to denote that is to use differential notation, and we write dy dx. dy dx is an equivalent notation, but in many ways it's a more useful notation in some ways because it tells you what the two variables are, what the independent and dependent variables are. Tells you that y is a function of x, and you're talking about the change in y with respect to the change in x, like that. Now, some more notation here that I want to kind of introduce today. This notation right here, this is called operator notation. And operator notation is just d over dx. And that is meaningless by itself. If you just write down d dx, that's a meaningless a thing to write down. And the reason why is because d dx is an operator. This notation is telling you to do something, telling you to do something. And what it's telling you to do is it's telling you to find the derivative of whatever function follows. See, and so if there is no function that follows, then it doesn't mean anything, right? So an operator has got to have something to operate on. And so in this case, when we write d dx, we're talking about find the derivative of whatever comes right after that d dx, okay? All right, so for example, if you have d dx, and then I put brackets right after it, and then I put Bob right after that, like that, that is saying find the derivative of Bob. Whatever Bob happens to be. We're assuming Bob is some kind of function. And so that's what that d dx of Bob is telling us to do, is find the derivative of Bob. All right? All right, so now what we want to do is we want to write down some properties for derivatives and calculating derivatives. And that's in particular what we're talking about here, is we're talking about calculating derivatives without having to use the limit definition that we talked about in the last screen and that we talked about in class in the last lecture. All right, so these properties go like this, that the derivative of a constant, first of all, we actually talked about that some in class in the lecture on Monday, that the derivative of a constant is always 0. So when I write d dx of c, I'm saying the derivative with respect to x of c. C is a constant, then the derivative with respect to x would be equal to 0. Right? The derivative of a constant is always 0. The next property, the derivative of x, we talked about this some in the lecture the other day. The derivative of x is 1. Right? If you're taking just the derivative with respect to x of x, then this is equal to 1. All right, the derivative of mx plus b, so of a linear function, derivative of mx plus b is equal to m. Right? That the derivative of a linear function is always just the slope of whatever that line happens to be. And finally, on this page, and this is an important property, that the derivative of a constant times a function, like that, right? The derivative of a constant times a function is equal to the constant times the derivative of the function. That's important for us. That is saying that if you take the derivative of a constant times a function, that the constant just trails along for the ride, essentially, in the process, and it doesn't really affect how you calculate the derivative. So that you can always take a constant outside of the differentiation if it's a factor, constant factor. It's got to be multiplication. All right. The next property, so there's 4 very basic properties right there. And let me highlight this so that for those of you who are looking back through these notes at home, that you can see or pick these properties out if you're going back looking for them. All right, so on the next screen, properties continued. Or we might just say more properties. And the next property goes like this, that the derivative of an addition or subtraction problem, the derivative of an addition or subtraction problem is simply the derivative of the first term plus or minus the derivative of the second term. This is a really good property, and it goes very much along with limits, because limits have this property also. And so that this is important for us, the fact that we can differentiate a function term by term. So if we have an addition or subtraction problem, we just take the derivative of each term separately and then add the results. All right, the next rule, so that's sometimes called the sum difference rule, by the way. This next rule, probably the single most important rule that you'll encounter in calculus, ultimately, and this is actually given a name. This is called the power rule. To be honest with you, are not going to go through and prove the power rule at this point. We just don't have the time to do that. We will talk some as we go through some specific examples of why the power rule would be a reasonable result. But the power rule has to do with how you take the derivative of a power of x. Right? How you take the derivative of x raised to the nth power. And this rule is actually n can be any real number. Now that's a very difficult statement to prove. It's actually not as bad to prove using integers. If n was an integer, you can use mathematical induction. If n is a real number, it's a very hard proof. But we're going to go ahead and state this, that this is true where n is any real number. And the property goes like this, that the derivative of x to the nth power is simply n times x to the n minus 1. And so notice what happens is that the degree of the variable starts out at n and ends up being n minus 1, that the degree of the derivative is always 1 less than the degree of the original function. If it's a polynomial, that the derivative of a polynomial function will always be degree 1 less than the original function, that will always be true. All right, so now with the power rule and the sum difference rule, and then some of the rules we talked about on the previous page, we can differentiate a lot of different kinds of functions and find derivatives for those pretty efficiently using these rules. So let's look at some examples now. All right, so if we have f of x, so this is an example right here. If f of x is equal to x cubed, right? So we have this third degree function right here. Then the derivative of this function, f prime of x, using the power rule, right? This is a power rule problem. And that power rule says that you bring the power down in front as a factor, and that this would be 3 times x squared. That the derivative of x cubed is the function 3x squared. That the derivative of a third degree function is a second degree function. Now I think at this point it probably would not be bad to talk about these two functions right here graphically and show you why this wouldn't be reasonable that this would be true. So now I could use my app to graph this, but these are easy functions to graph by hand. So let's go ahead and do that. And let me make the scale just a little bit bigger. Like that. And so our cube function, all right, that's our function that we're looking at here. We know goes through those 3 points, and then has a graph that kind of looks like this. And probably make that a little bit flatter. Okay, so there's our cube function. There's x cubed. And then 3x squared, which is its derivative, we'll put that in blue in a different color. Well, and let's first of all talk about the tangent lines here for this graph. The tangent lines, notice, are, let's see, so tangent lines are always sloped upwards. Actually, except at one x value, but we'll talk about that in a second. And so that means that the derivative should always be positive. All right, and then what it happens is it looks like, and now I didn't draw this extremely well in the middle here, but what looks like happens here is that the graph kind of levels off and that there's actually a horizontal tangent line right in here. So we expect here that the derivative, there should be a horizontal tangent at x equals 0. So there should be a horizontal tangent at x equals 0. And so that means that the derivative should be 0 when x is equal to 0. All right? And then also notice that the derivative, or that the tangent lines notice, even though that they're slanted upwards, that like if you look at a tangent line right there, at that value and this tangent line way over here, like so, that it looks like the derivative is getting steeper and steeper over there. And the same thing in the other direction, that the derivative is getting steeper in this direction also. So all those things, if you kind of piece them together, indicate, and look at the graph of this function. Here's 3x squared. Here's the graph of the derivative function. And I'm putting this in blue. And notice how that makes sense in terms of the red graph and the slopes of the tangent lines on that red graph. that the derivative, first of all, is always positive, right? It's always above the x-axis, that it's 0 at x equals 0, and that it gets bigger and bigger and bigger, the bigger the x values are, or the smaller the x values are. And that implies that there's very steep tangent lines to this graph, which the cubed graph has very steep tangent lines. And that the shallowest tangent line is right there in the middle for that x cubed function. It's right here at 0, 0. And it looks like that's the shallowest tangent line, that all the other tangent lines are going to be bigger. And that's exactly what the derivative graph looks like, is that the smallest value in the derivative graph is when x is equal to 0. So that blue graph seems to fit in really well with that red graph as being its derivative, right? So it kind of is reasonable that that's what we would get. All right, so let's look at more examples now of the power rule and the other rules that we were talking about. So the next function I want to look at is g of x equals x to the 10th. So this is another power function, and so this is just simply a power rule problem. And so g prime, using the power rule, we bring that exponent down in front as a factor, and then we subtract 1 from the exponent, and so this derivative should be 10x to the 9th. All right. Now the next one, the next function we're going to look at, we have h of x equals 5x to the 7th. So now notice this function has a constant factor. So if we were taking the derivative of this function, if we were taking the derivative of 5x to the 7th, using differential notation, operator notation here, the derivative of 5x to the 7th should be 5 times the derivative of x to the 7th, that the 5 just kind of comes along for the ride. And then the derivative of x to the 7th is the power rule, so that's 7x to the 6th. And so then you'd end up with 35x to the 6th. And so that's our derivative here. H prime of x would be 35x to the 6th. Using a combination of the constant factor rule and the power rule right there. All right, now remember I said that the power rule works for any real number value for the exponent. So if we have f of x is x to the 2/3, even though that's a rational exponent, that the power rule certainly still is valid in this case. And we get that f prime of x is equal to, using the power rule, you bring the 2/3 down in front as a factor, and then you subtract 1 from the exponent. So 2/3 minus 1 is what you get as the exponent right there. And so f prime of x would be 2/3 x to the negative 1/3. Or getting rid of the negative exponent, you'd have 2 over 3 x to the 1/3. Now notice in this particular case, one thing I want to point out is that the derivative of this function is not defined at 0. If you try to find f prime of 0 here, notice you get 2 over 0, so that does not exist. And so we say that f prime of x does not exist when x equals 0. The function's not differentiable at 0. Remember, that's the way you might, the fancier way of saying it, that it's not differentiable at x equals 0. And to look at why that might seem reasonable, look at the graph for x to the 2/3. If you look at the graph for x to the 2/3, what you get here is that the graph goes through 1, 1 and negative 1, 1, goes through 0, 0, and you get a cusp like that. And so it makes sense that this differentiability that the function would not be differentiable when x is equal to 0. Remember, this kind of point is called a cusp, and the functions are not differentiable at cusps, right? We'll always get a place where the derivative does not exist. Remember, there's a vertical tangent line to that graph at that point. So there's a vertical tangent line there. All right, so that makes sense then. The derivative we get, that the power rule gives you a function that's not defined when x is equal to 0. So based on the graph, it definitely makes sense that that would be true. All right, let's go on to the next example then. All right, so on this next example, we have f of x equals the 4th root of x. Now, as a root, we don't really have any properties that directly talk about roots here, but what we do have is the power rule. And so remember that you can always take a root and write it as a power. And that's what you would do first in this problem, is you'd write 4th root of x as x to the 1/4 power. And then you could use the power rule. And f prime would be, bring the exponent down in front as a factor, so you have 1/4, and then x to the 1/4 minus 1 power. Remember, you subtract 1 from the exponent. And so f prime of x would be 1/4 x to the negative 3/4. I do not want you to leave it like that. I do not want negative exponents in a derivative typically. And so get rid of that negative exponent, rewrite this as a fraction. And so you have 1 over 4x to the 3/4, like that. All right. If you write it as a radical, you can. I would just assume you just leave it as an exponent in that particular problem. All right. The next example, f of x. So we're looking at lots of different problems and just kind of walking through how we would apply these properties in these different problems. So in this next one, you have f of x is x plus 1 over x to the 6th. So first of all, we have an addition problem. So remember, we have a property that says you can take the derivative of an addition problem by just taking the derivative of each term individually. So that's what we'll do here, is we'll take the derivative of each of these terms individually. But that's okay to do. The other thing is we want every term to be something that we can actually calculate the derivative for. The x is not a problem, but the 1 over x to the 6th is definitely a problem because it's not really written as a power. And so you want to rewrite this function first so that everything is just x to a power. So rewrite so you can apply the power rule. Right? And now you can find the derivative of each one of those terms. So f prime of x here, the derivative of x would be 1. And then the derivative of x to the negative 6th, use the power rule. So I write this 6, the negative 6 is a factor in front of the x. And then remember, you are subtracting 1 from the exponent. So this is negative 6 minus 1. And so f prime of x would be 1 minus 6x to the negative 7 power. Remember what I just told you in the last problem? I want you to rewrite these without negative exponents. So this would be 1 minus 6 over x to the 7th. I think in some cases it would be good to get a common denominator in a problem like this. And so the common denominator would be x to the 7th, right? So you'd multiply this first fraction by x to the 7th over x to the 7th. And so our derivative would be x to the 7th minus 6 over x to the 7th. That's our derivative for this function. Like that. Okay, so the general rule here, and this you're not going to like this general rule probably because it's too nebulous, but it's the best we can do as far as I'm concerned here, and that is simplify algebraically when reasonable. And that's the kicker right there, is what does that mean when reasonable? And that just depends on the problem, to be honest with you, as far as when it's reasonable or maybe not necessarily reasonable to simplify. And so you're just going to have to make some judgment calls occasionally on how you want to simplify an expression, okay? Or how much you need to simplify an expression. All right, and it's going to be common, by the way. You're going to calculate a derivative, and then you're going to check your answer in the back of the book, and the back of the book's answer is going to look really different than your answer. And so the question is going to be, well, how do you get that answer? And, sometimes the hardest part of the problem is not the calculus part of it, but sometimes the hardest part of the problem is the algebra and trying to match up your answer for a derivative with the textbook's answer. All right, so let's continue on. We're doing a good job here. The next example, so you have f of x is x to the 5th plus 3x cubed plus 6x squared plus 8x minus 9. Okay, so this is a 5th degree polynomial. It's a bunch of addition and subtraction problems. And so remember the sum difference rule says that you can take the derivative of each term separately. So that's what we would do here. So f prime of x, the derivative of x to the 5th using the power rule would be 5x to the 4th. Now the 3x cubed, well, the 3 at the beginning is a constant factor, so we have that constant factor rule. So that 3 just comes down for the ride right there. And then we take the derivative of x cubed, which is 3x squared. We do the same thing with the next term. The 6 just comes down for the ride. It's a constant factor, and we take the derivative of x squared using the power rule. That would be 2x to the first power. The derivative of 8x, well, the derivative of x is 1, and so this would just be 8 times 1. And then finally, the derivative of 9 would be 0. So you can put 0 there at the end if you want. All right, and this 8 just came down for the ride also. So constant factors just kind of come down for the ride with this type of derivative. Now you obviously don't leave it like this. You clean this up. And so this would be 5x to the 4th plus 9x squared plus 12x plus 8, like that. And so that would be our derivative function in this case. And in practical terms, most students are going to skip that middle step and write it directly as the derivative at the end right there, which I think is reasonable that you would be able to do that. So in this function, f of x equals negative 6x cubed plus 3/5 x squared minus 1/4 x plus 8. If we wanted to calculate the derivative of this function, very similar to the last problem. Just first of all, it's a bunch of addition and subtraction, so you're differentiating each term separately. And then you're just using the power rule on each of these terms. So f prime of x, but I'm going to skip over that middle step that I used on the previous example and go right to the derivative. So the derivative of negative 6x cubed would be negative 18x squared, right? We bring the 3 down in front as a factor, and then times negative 6 would be negative 18. And then 3/5 times x squared, you bring the 2 down in front as a factor, times the 3/5 that's already there, and that would give you 6/5. And then subtract 1 from the exponent, so it would be x to the 1st. The derivative of negative 1/4 x would be minus 1/4. And the derivative of 8 would be 0. And so there's our derivative for this particular problem. All right. We're working a lot of different kinds of examples here. So let's look at this one. The powers are a little bit messier here. You have 4 times the square root of x plus 3 over x to the 10th minus 1 over the 5th root of x cubed, like that. All right, so if you were going to try to differentiate this, first of all, it's a bunch of addition and subtraction, so that's not a big deal. We differentiate each term separately, but the problem here is that you've got a bunch of terms that you've got to write as powers first if you want to write or use the power rule. So we got to take a step here that's not a derivative step. Take 4 times the square root of x and write that as 4x to the 1/2 power. And then 3 over x to the 10th, I would write that as 3 times x to the negative 10. And then the 5th root of x cubed is x to the 3/5 power. So this last term would be x to the negative 3/5, like that. All right, so write each term so you can use the power rule. Write each term so power rule can be used. Right, and so that's what we did in this step right here. And so now you're ready to differentiate. So g prime of x. All right, so what do? You take the exponent, you write it down in front as a factor. So 4 times 1/2 would be 2, and then subtract 1 from the exponent. So this is 1/2 minus 1. All right, the next term, bring the exponent down in front as a factor. So that negative 10 times 3 would be negative 30 x to the, and this would be negative 10 minus 1 power. And then finally, in the last term, we bring the negative 3/5 down in front as a factor. So that would give me a positive 3/5. And then this would be negative 3/5 minus 1 right here. All right, so please be careful about the arithmetic. It's really common to see students mess up the arithmetic on a problem like this. So you want you to really be careful. So you have 2x to the negative 1/2, 1/2 minus 1, minus 30x to the negative 11, and then finally plus 3/5 times x, and that's negative 3/5 minus 5/5, so that would be negative 8/5 right there. And then recall that I said get rid of the negative exponents. So this would be 2 over x to the 1/2 minus 30 over x to the 11 plus 3 over 5x to the 8/5. And this would be a good example of a problem where getting a common denominator there is really not a really reasonable exercise because it's a messy common denominator, and so I would just leave that answer just in that form, to be honest with you. All right, so let's look at a couple more problems, a little bit of some changes here a little bit. Next problem, let's say we are given this function f of x equals 2 times x minus 4 squared. And the directions here were to write the equation of the tangent line when x is equal to 2. All right? So the first thing you'd want to do probably is find f of 2 in this problem. So f of 2 is 2 times 2 minus 4 squared. So 2 minus 4 is negative 2. Squared would be 4 times 2 would be 8. So f of 2 is equal to 8, and we're talking about the point 28 on this graph. All right, so now what we need to do is find the slope of the tangent line. So now find the slope of the tangent. And to find the slope of the tangent, that means we want to find f prime. Well, now find the slope of the tangent when x is equal to 2. So that means we want to find f prime of 2 in this function. All right, so the first thing we're going to do is find f prime. So first, find f prime. So to find f prime, I've got that, what can I take derivatives of based on the properties I have so far? Well, I can take derivatives of addition and subtraction problems. I can take derivatives of constants times functions. I can take derivatives of powers, but this powers of x. But this function is the power of x minus 4. So what we got to do first is write this in a form where we can calculate the derivative. So we square out that x minus 4. So this would be 2 times x squared minus 8x plus 16. Now the 2 at the front, now we're ready to calculate the derivative. That 2 at the front is a constant factor, so it does not affect anything, and it just comes down for the ride. So you could leave that there if you wanted to. Or you can multiply it through and then calculate the derivative. Either way would be okay. But I'm just going to leave it sitting out in front because it's a constant factor. Let me write this constant factor there. And so now I just take the derivative of what's inside the parentheses. So the derivative of x squared using the power rule would be 2x. And then the derivative of negative 8x, power rule, would be negative 8. Derivative of 16 would be 0. And so that would be my derivative right there. And if you want to multiply this out, you can, 4x minus 16. So now what do? Well, we calculate f prime of 2. So f prime of 2 would be 4 times 2 minus 16, or negative 8. And so what does that negative 8 represent? That's the slope of the tangent line. And it's the slope of the tangent line at the point 28. Right, so now the equation of the tangent line, what do we have? We have a point, right? We calculate the point, and now we've calculated the slope right here. And so we've got a point and we've got a slope, so we can use the point slope form for the to write out the equation. And so you get y minus 8 equals negative 8 times x minus 2. Right, using the information we calculated in this problem. So that gives us y minus 8 equals negative 8x plus 16. And then add 8, you get y equals negative 8x plus 24. And that would be the equation of the tangent line at that particular point. All right, you will be asked on this first exam to write down some equations of tangent lines, or at least one. And it's an important skill. It's something you're going to have to be able to do. And for one thing, it emphasizes that derivatives are slopes of tangent lines. Right? And it's always, as we go through all these calculations, it's kind of easy to lose sight of the fact that that's what you're finding. All right, the next example. Let's take h of x. This is a function, and now we just want to find h prime here. And this is the function 4x cubed plus 2x plus 5 divided by x squared. All right, so again, we know how to calculate derivatives of addition and subtraction problems. We know how to calculate derivatives of powers of x. This is a division problem, and so to calculate this derivative, it's not in a form where we can calculate the derivative using the properties that we have. And so can you use algebra? So that's the question. Can we use algebra to rewrite so we can use the power rule. Power rule and the sum difference rule. And in this problem, yes, we can do that because this is just a single term in the denominator, we could actually divide this out term by term. So that's what I do. I divide each term by x squared. So I can do the algebra here in this problem. And then simplify each of those fractions. So h of x would be 4x plus 2 over x plus 5 over x squared. And then use negative exponents so that we can use the power rule. So you have 4x plus 2x to the negative 1 plus 5x to the negative 2. And so now we go through and we can calculate the derivative. So the derivative of 4x is 4. The derivative of 2x to the negative 1. So we use the power rule there. So bring the negative 1 down in front as a factor. This would be negative 2x to the negative 2. Subtract 1 from the exponent. And then in the last term, we use the power rule. Bring the negative 2 down in front as a factor. So that would be negative 10x to the negative 3. Subtract 1 from the exponent. So h prime of x is 4 minus 2 over x squared minus 10 over x cubed. And, that's okay to leave it that way. The LCD in this case, the LCD is x cubed. And so if you did need to get a common denominator there, you could multiply the first fraction by x cubed over x cubed, the second fraction by x over x, and then you'd have x cubes in the denominator of each of those fractions. And you really need to know how to do this, certainly, get a common denominator. So you have 4x cubed minus 2x minus 10, all divided by x cubed. And so that would be our final answer there. All right. So we're going through and learning how to calculate derivatives. The next derivative we would like to look at here, we're going to look a little bit at trig functions. The textbook doesn't quite do this in the order that I'm doing this in. So we are covering the material out of 3.3, 3.4, and 3.5. Not quite in the order that the textbook has got it in, by the way. But that's okay. It's all the same material, certainly. So the next thing we want to do here is turn our attention to trig functions a little bit. And look at some derivatives of trig functions. So if we were going to look at f of x equals sine x, right? Now I'm going to write down the derivative here, and then we're going to look at this graphically to see why this would kind of make sense. We're not going to use, you could actually use the definition, the limit definition of the derivative, and then some fancy algebra and trig to calculate this derivative and prove that it's true. We're just going to look at the graph and see that it's reasonable. That if f of x is sine x, that f prime of x, the derivative of sine x, is cosine x. And the derivative of cosine, if f is cosine x, its derivative is the negative of sine x, like that. So let's look at that first one and see why that would be reasonable. Think about the graph of the sine function. Now I'm going to make a rough sketch of the sine function here. So let's say that this is 1 and this is negative 1 down here. And I'm going to scale this off by pi over 2s. Like so. So this is 5 pi over 2 right here, and then 3 pi. This is 7 pi over 2, and then finally 8 pi, right, or 4 pi right here. 8 pi over 2, which is 4 pi. So I've got enough room there to sketch 2 cycles of the sine function. So the sine function, this is not exactly, not exactly to scale, but gives you, this should be a very familiar graph to you. You should definitely know this graph because should have talked about this a lot in previous classes. This is a fundamental graph for a calculus student. We're certainly going to use this graph and its properties to our advantage frequently. So that's the graph of the sine function right there over 2 periods, 2 cycles of the graph. And so what do we have? Let's look at the tangent lines to this graph. So first of all, where are there horizontal tangents? Let's write that in red, that question. Where does this graph have horizontal tangents? Wherever it has horizontal tangents, the derivative of this function should be 0. Derivative should be 0. And so that means the derivative should have an x-intercept. So the derivative should have x-intercepts at these places because it's equal to 0. It should be crossing the x-axis. So we'll put those places in, well, first of all, so where are there horizontal tangents? Well, there's a horizontal tangent here at pi over 2, another one at 3 pi over 2, another one at 5 pi over 2, at 7 pi over 2, and so on. And so what do you have there? That the derivative graph better be 0 at those spots, at those x values. So I'm putting some heavy blue dots there. And those are places where the derivative graph should be crossing the x-axis. And then if you look at how the tangent lines are sloped on that sine graph, right, what are they saying? That the graph, that they're sloped upwards until you get to pi over 2. And so if they're sloped upwards, then the derivative should be positive. And then from pi over 2 to 3 pi over 2, in this interval, they are sloped downwards, and so the derivative should be negative. Right? And that just keeps on going like that cycle. So slanted upwards in that interval from 3 pi over 2 to 5 pi over 2. And so the derivative should be positive. Then the derivative, these are slanted downwards again. So the derivative should be negative, and so on. Right? Positive here. So when I say negative and positive down there, what I'm saying is that the graph should be above the x-axis or below the x-axis. If it's positive, it's above. If it's negative, it's below. So the graph of the derivative should be above x-axis, below the x-axis, above the x-axis, below the x-axis, above the x-axis, and so on. Finally, where does the sine graph have its steepest tangent lines? Well, it has its steepest tangent lines, and I'm going to put those dots in pink at the origin, and then at pi 0, 2 pi 0. That's where it's steepest. And so that's where it gets to have maximums and minimums. And so if you put all those things together, then what you're getting is the cosine graph, right? So if we could put that graph in, I'll put it in pink here. So the cosine graph fits all of this information exactly like we're talking, right? It's above the x-axis, now it's below the x-axis, and now it is above, has a maximum here, and then is below, comes back down, and then it's below the x-axis until you get to 7 pi over 2, and then it's above the x-axis, and so on. And it had the maximums and minimums fit perfectly also. Whoops. And so that cosine graph fits in really well with the sine graph, that would be the derivative function. That if sine x is f of x, then cosine of x is f prime of x. That it describes its derivative really well. You could go through the same kind of analysis with the cosine graph, certainly, and get the same thing. So, all right, so these are rules now. These are things that, from now for the rest of your calculus lives, you're saying that you know that the derivative of the sine function is the cosine, and that the derivative of the cosine function is the sine. The derivative of the cosine function is the negative of the sine, I should say. All right, so let's look at some examples here. So if we have g of t is pi cosine of t, then pi is a constant, so g prime of t, that pi just comes down for the ride, and then the derivative of cosine of t is negative sine t, like that. So g prime of t would be negative pi sine of t. Right, so the derivative, if g is pi cosine t, g prime is negative pi sine t. All right, let's say we have this example. Let's say we have f of x is 5 sine t minus 6 cosine t. That's our function. Then the derivative of this function, f prime, would be the 5 and the 6 just come down for the ride. And so the derivative of sine is cosine. So this is 5 cosine t. And then the derivative, the negative 6 comes down for the ride. And then the cosine, its derivative, is negative sine t. And so notice that last term actually, whoops, I think one thing I messed up on here a little bit, and I just noticed this just now. This should be f. These should all be functions of t right here, so I needed to write it that way. So this is f of t, and this is f prime of t, like that. So f prime of t, just cleaning this up a little bit, would be 5 cosine t plus 6 sine t, like that. All right, so now the next problem I want to look at, g of x is equal to x squared times sine x. Now, we've talked about differentiation for addition and subtraction problems. We've talked about differentiation when you have a constant factor. We've talked about differentiations where you have a power of x. But this does not fit any of those because this is a multiplication problem. And so this is a product. This is a multiplication problem. And so the question is, how do you take the derivative of a multiplication problem? And, right, so that's the question. How do we calculate the derivative of a multiplication problem or of a product? And this isn't as simple as with addition and subtraction. Addition and subtraction followed along very much with limits, where you could just take the sum, the limit of a sum or a difference. You can take this derivative of a sum or a difference. But multiplication is not the same. The derivative of a multiplication problem is summarized in what we call the product rule. And the product rule goes like this, that if you're going to differentiate a multiplication problem, like f of x times g of x, that's a little, it's not just the derivative of f times the derivative of g. Definitely not equal to that. What it is equal to is, the first function times the derivative of the second function, so the derivative of g, plus the second function, g, times the derivative of the first function. And I usually just keep the order the same here. So I'll put brackets around those functions so it's separate like that. So it's f, if you write this as prime notation, it would be f of x times g prime of x plus f prime of x times g of x, like that. So you write down two different terms and you just take the derivative of a different factor in each term is basically what you're talking about doing. So it's not necessarily a hard rule to remember because of that pattern. And by the way, this rule would extend over to however many factors. So if you have let's say that f of x is g, the function g times the function h times the function m, 3 factors. Then f prime now would have 3 terms in it. And all I would do here is I would just write g, h, and m multiplied, g, h, and m multiplied, and g, h, and m and multiplied. And all you're doing in each term is you're taking the derivative of a different factor. So this is g prime in the first term, h prime in the second term, and m prime in the third term, like that. So that would be an easy way to remember how you calculate the derivative if there's 3 factors. All right, so looking at our function, so now we can calculate this derivative, that the g of x is x squared sine x means that we have g prime would be the first factor, x squared, times the derivative of the second factor. And I'm going to go ahead and write this out in operator notation at the beginning here. So it's the first factor times the derivative of the second factor. So that's d dx of sine x, plus the derivative of the first factor, derivative of x squared, times the second, sine x, like that. And then actually calculate those derivatives. And so you have x squared times cosine x plus 2x times sine x. And that would be our derivative. All right. So let's see. Let's look at one. So there's our example. Let's look at an example here where you have h of x is x to the 4th times sine x times cosine x. So this one has, this function has 3 factors. And so what you're doing here is you're just calculating the derivative of a different factor in each term, and there's going to be 3 terms here. So h prime of x would be the derivative of x to the 4th times sine x cosine x, plus x to the 4th times the derivative of sine x times cosine x. And then finally plus x to the 4th sine x times the derivative of cosine x. Like that. So you notice in each term I'm taking the derivative of a different factor. I'm highlighting where I'm calculating those derivatives in each one of those terms. All right, so, and then clean that up, actually do the differentiation. H prime would be, first term would be 4x cubed sine x cosine x. Second term would be x to the 4th times cosine x times cosine x. And then the last term would be x to the 4th times sine x times negative sine x. Now I might certainly might clean that up a little bit. So you have h prime of x would be 4x cubed sine x cosine x plus x to the 4th cosine squared x minus x to the 4th sine squared x. Now there are some trig identities you could use to simplify that maybe a little bit, but I'm just going to leave that at that point. Now, one thing you should get in the habit of doing is if there's an obvious common factor, like in this case, there's an x cubed that's a common factor. That's not a bad thing to do, is to factor out that common factor. And I'm going to do that here on this problem. Right, and leave it in factored form. Factored form is probably not a bad form to have this in. So, all right. So now we know how to take the derivative of a multiplication problem. Let's look at division problems. So if you have f of x is g of x over h of x, right? This is a division problem right here. To calculate the derivative here, we use what we call the quotient rule. Again, we're not going to prove the quotient rule at this point, but we're just going to state it, and we'll certainly talk about why it's reasonable. So if you wrote this in operator notation, the derivative of g of x over h of x would be h of x, the bottom function, times the derivative of the top function, minus the top function, g of x, times the derivative of the bottom function. And that would be all divided by, so this is a complicated expression, h of x squared, the bottom squared. So the way I say this in words is it's the derivative, it's the bottom times the derivative of the top, minus the top times the derivative of the bottom divided by the bottom squared. Right, so that's the way I'll say it. So bottom times the derivative of the top minus the top times the derivative of the bottom and then this would all be divided by bottom squared. All sorts of different ways you could remember that I've seen. And, some people have little songs that they sing or little rhymes. You definitely don't want me singing it. You would never remember the quotient rule if I tried to sing it. So, however you're going to write this out, you just need to remember the quotient rule, definitely. All right, so example, let's look at some examples here. So you have f of x is 3x minus 1 over 5x plus 2. 3x minus 1 over 5x plus 2. So definitely a quotient. Not reasonable to divide that out. So we're going to use the quotient rule on this problem. So f prime of x would be the bottom function, 5x plus 2, times the derivative of the top function. And I'm just going to write that out as the derivative of the top function. So d dx of 3x minus 1 minus the top function times the derivative of the bottom function, derivative of 5x plus 2. Let's see, I'll use brackets here to be consistent. And then that would all be divided by the bottom function quantity squared, like that. So you have two derivatives here to calculate. You have the derivative of the top right there, and then the derivative of the bottom right there. So you've got to go ahead and calculate those derivatives. So f prime would be 5x plus 2 times the derivative of 3x minus 1. The derivative of 3x is 3. Derivative of 1 is 0. And then minus 3x minus 1 times the derivative of 5x plus 2. Derivative of 5x is 5. Derivative of 2 is 0. And then this would all be divided by the denominator squared, like that. Definitely want to simplify this. So f prime of x would be 15x plus 6 minus 15x Be careful of the signs here. This is going to be plus 5, all divided by 5x plus 2 squared. And so then you get 11 over 5x plus 2 squared. Like that. All right, and now on Monday's lecture, we'll look at some at graphs of these functions and how the graph of the derivative function that we're calculating fits in really well with what the original function looks like. You know, for now, we're not going to do that because right now we're concentrating on actually calculating derivatives. So, but we'll look at some graphs next time. All right, next example. Let's look at this function. F of x is 3x to the 4th over x squared minus 1. All right, so definitely a quotient rule problem. And so f prime of x, we're going to calculate the derivative here, would be the bottom function, x squared minus 1, times the derivative of the top function, the derivative of 3x to the 4th. And then that would be minus the top function, 3x to the 4th, times the derivative of the bottom function. So that'd be the derivative of x squared minus 1. And that'd be all divided by the bottom function squared, like that. So once again, I've got some derivatives to calculate in here. The derivative of 3x to the 4th, the derivative of the top right there, and the derivative of x squared minus 1, the derivative of the bottom on that one. So f prime of x would be x squared minus 1 times 12x cubed. And then that would be minus 3x to the 4th times 2x. And that'd all be over x squared minus 1 squared. And there'd be no reason to square that out. I'd just leave that part alone. All right, so f prime of x, let's see if we can simplify this a little bit. We get 12x cubed times x squared minus 1 in the first term. And the second term would be 6x to the 5th. When we multiply those terms like that, over x squared minus 1 squared. And, you know, what you might do in a problem like this is you might actually factor out in the numerator. There is a common factor there of 6x cubed that you can take out of those two terms. And if you take out a 6x cubed, you're left with 2 times x squared minus 1. And then in the second term, you're left with just x squared. Okay. And this would be all divided by x squared minus 1 squared, like that. And so a little bit left to do to simplify this thing. You have 6x cubed times in brackets 2x squared minus 2 minus x squared over x squared minus 1 squared. And so then collect like terms inside the brackets, and you get 6x cubed times x squared minus 2 over x squared minus 1 squared. So that's the derivative. That's kind of a messy problem there, definitely. So. Okay, let's look at a problem. We're going to look at maybe just a couple more problems here to finish up with what we want to do today, and that'll leave us with talking about velocity next time and higher order derivatives some also before we actually start in on the chain rule. So on the next problem, so this one's, you know, that last one was a messy derivative. This is actually, unfortunately, going to be a little bit messier. So you have the square root of x plus 1 divided by the square root of x minus 1. All right, so if you're going to go ahead and take the derivative here, first thing is I want this written as powers. So this is x to the 1/2 plus 1 over x to the 1/2 minus 1. Right? Because you're going to be using the power rule in here. You definitely don't want to leave those radicals in there. All right, so f prime, I'm going to leave myself a lot of room here because there's going to be a lot of algebra to do here. Using the quotient rule, this would be the bottom function times the derivative of the top function, and I'm not actually going to do the differentiation in this step, minus the top function times the derivative of the bottom function, and that'd be all divided by the bottom function squared, like that. All right, so we've got two derivatives to calculate. That's always going to be true with the quotient rule. You have those two derivatives in the numerator to calculate. So f prime of x, you have x to the 1/2 minus 1, and the derivative of x to the 1/2 plus 1. Right, power rule. Derivative of x to the 1/2 would be 1/2 x to the negative 1/2 because you're subtracting a 1 from the exponent. The derivative of 1 is 0. So that's it, 1/2 x to the negative 1/2. And then minus x to the 1/2 minus 1. And the second derivative here is the exact same as the first one. No difference in the two because the only place they were different was in the constant. Okay, good. So we have made it through the calculus of this problem. The rest is algebra. So this is the calculus right here. And then from here on, it is algebra. And the algebra gets messy on this problem. So what I would do is I would see that I do have a common factor in the numerator of this fraction here because I've got 1/2 x to the negative 1/2 and 1/2 x to the negative 1/2 is in both of those terms. So I could factor that common factor out. That's definitely what I would do here. And when you take that thing out, you're left with x to the 1/2 minus 1 minus, be careful with the signs of the terms here, and then minus, put in parentheses, x to the 1/2 minus 1. All divided by this thing squared. And I just keep on writing that down over and over again. There's nothing to do with that. You don't want to square it out at all, so you just leave it like it is. And then, distribute this minus sign through right here. And so f prime of x. Now, okay, let's look. You have this x to the 1/2 minus 1 squared in the denominator, but I have a 1/2 in the numerator, so that gives me a 2 in the denominator. And then that x to the negative 1/2 comes to the denominator as x to the positive 1/2. So that stuff gets written in the denominator. And then in the brackets in the numerator, the x to the 1/2s cancel. And let's see, I think, yeah, I did make a slight mistake here. That's okay. There's a plus sign there, and then I didn't carry it over. There should be a plus sign there. That's a mistake. And so then this plus sign carries down here. That should be a plus sign. Okay, so that's better. So the x to the 1/2s cancel, and then you have negative 1 minus 1. You're left with a negative 2 in the numerator. And then finally, the 2's divide out, and so you're left with negative 1 over x to the 1/2 times x to the 1/2 minus 1 squared. And there's our derivative. And that's a yucky problem. If you want to write things as radicals, like the original problem was, you could. you'd have the square root of x times the square root of x minus 1 squared, like that, as our derivative. All right, so let's talk about some more trig functions here before we shut this down for the day. So we have, remember, we have if f of x is sine x, that the derivative is cosine. And we have that if f of x is cosine x, then the derivative is negative sine. So what we need to do to finish this is we need to talk about the tangent function. And so what's f prime for the tangent? And we need to do the same thing for the secant. Those are the more important ones of the ones we have left. And then we'll also talk about the cotangent and the cosecant. And actually just kind of fill in the blanks on those. So I want to fill out this little chart so I have all these derivatives also. So I have the derivatives of all 6 of the trig functions. So the tangent, we're going to go ahead and actually prove it. If f of x, well, let's write it this way. That if we're looking at the derivative of the tangent function, that would be the derivative of the sine function divided by the cosine function. And that's the sine function in the top there. I'm going to clean that up a little bit. So this is, in fact, a quotient rule problem. We could use the quotient rule to do this, to actually verify this. So the quotient rule, this would be the bottom function times the derivative of the top function minus the top function times the derivative of the bottom function. And this would be all divided by the square of the bottom function, like that. And so what you get here is you get the cosine of x times the cosine of x, the derivative of sine is cosine, minus the sine of x times negative sine of x, because the derivative of cosine is negative sine, all divided by cosine squared. And when you simplify the numerator, you actually get cosine squared x, and then you get plus sine squared x over cosine squared x. And that's a trig identity. That's a Pythagorean identity. That's just 1 over cosine squared. So it really simplifies a lot. And then cosine squared, 1 over cosine squared, can be written as secant squared x. And so that's our derivative right there, is that this is secant squared x up at the top. Now, with the secant, if we're going to prove the secant, we could do something similar. But with the secant, we'd write it as 1 over cosine, and then we might use the quotient rule there to calculate the derivative. And what we would get is you have to do a little bit of messing around with the factors at the end, but the derivative of secant is secant tangent. And then the derivative of the cotangent goes along with the tangent. The derivative of the tangent is secant squared. The derivative of the cotangent is negative cosecant squared. And the secant and the cosecant go together. If the secant, its derivative is secant tangent, then the derivative of the cosecant is negative cosecant cotangent, like that. And so there's the derivatives of all 6 of the trig functions. All right. And then finally, very last thing to talk about here, just to mention this for a little bit at this point, higher order derivatives. And I want to write this down. These are derivatives of derivatives. And I want to look at a little bit at the notation here for this. So if we have f of x is sine x, then f prime of x is cosine x. That's our derivative of the sine. And the higher order derivative, f double prime of x, well, that's the derivative of the derivative. So that's the derivative of cosine, which is negative sine. The third derivative would be f triple prime. And that'd be negative cosine of x. And that would be, this would go on for like this. And then if you're going to go ahead and use differential notation here, so then if we have y as sine x, then the first derivative is dy dx, and that's cosine x. And the second derivative is written like this. It's written with exponents on that differential notation. Do not read that as exponents. Do not read that as d squared y dx squared. That's just read. So d squared y over dx squared. I want you to sound good in the math lab if you're talking about this, so I don't want you to say d squared because that's not what it is. It's not an exponent. Just read this. So read as the second derivative of y with respect to x. Right, that's how you read it. And then the third derivative, you'd use exponents of 3, and so on. Right, so I wanted to write a little bit about that kind of stuff. So let's see, if you had f of x is x cubed plus 2x squared minus 3x plus 8, then f prime of x would be 3x squared plus 4x minus 3. The second derivative of x would be 6x plus 4. The third derivative of f with respect to x would be 6, just a constant of 6. And then the fourth derivative, typically we don't use primes for the fourth derivative. You might see it sometimes with just the number 4 in brackets. The fourth derivative would be 0. And then all their other higher order derivatives after that would be 0. All right, so for homework then, what I would do for sure is work on 3.3 and 3.5 homework. We still have some material left to do out of 3.4. So I'm going to work on 3.4 next time. So next time, let's see, next time we're going to cover 3.4, talk about velocity sum, finish 3.5. We've really mostly finished 3.5 already. And then we're going to start in on 3.6 on the chain rule, right? So that's something we'll start next time on Monday. All right, remember that the exam 1 review is up. So be working on the exam 1 review, definitely. That's a big deal to start in on that. Remember that I have online office hours. Yesterday, I had online office hours for my college algebra class. I had 2 people get online with me at the beginning of my hour. And I worked with these 2 people for almost the entire hour on problems that they had. And so they got a lot out of that hour, where we just sat down and worked on questions that they had. So my online office hours, just to make sure that you've got these written down somewhere. So 9/21, that's Thursday, that's tomorrow, from 1 to 2. And then we've got Sunday, the 24th, from 7:30 to 9 p.m. And Then finally, the 25th, Monday, from 8 to 9 p.m. So please take advantage of those office hours. Come on by for help. Also remember that the extra credit assignment is due, extra credit and homework on 2.2, 2.3, and 2.4. These are both due on Friday of this week. That's the 22nd. And the extra credit assignment, remember, you can go to the first page of the lecture or the notes, either one of them from the last class period, and you can get what that extra credit assignment is, okay? So have a great day. Please be working on your calculus. Don't hesitate to come by my online office hours for help. Next week's a test week, so we've got a big week ahead of us next week. So please be working on the homework. Thanks, and have a great day.